All right, the next thing we're going to talk about is the relationship between free energy and temperature. This is the equation that we have used for determining free agency. I'm in sports all of a sudden. Free energy. And we've also stated that in order for us to be able to predict whether a reaction is going to be spontaneous or not, is the value of delta G must be negative or less than 0. If it's positive, then it's considered to be non-spontaneous. But let's look at how the relationship of these variables affect the overall spontaneity of the reaction. We start with delta H. As we can see, if we want a negative value here, if the delta H is negative and the delta S, which is measured in joules per mole Kelvin, and delta H is measured in kilojoules per mole, and the delta G is in kilojoules, then this is a very much larger quantity than this. Now, granted, we're going to multiply the temperature by the joules per mole Kelvin of entropy, but the value of the temperature has to be so exceedingly high to affect the change in delta H to make it from negative to positive that it's almost, or positive, negative, whatever, is going to be minimal. That effect is going to be minimal. So we know that if this is going to be a negative value, the odds are that it is going to create a negative value. So that means exothermic reactions will tend to be a leading cause for a reaction to be spontaneous. So exothermic reactions where delta H is negative, as we said, are basically the majority of natural reactions. If something occurs naturally, it's going to be spontaneous, and since most reactions tend to be exothermic, most natural reactions tend to be exothermic, then we would expect then that relationship to be true. So the delta G being negative relies heavily, but not completely, on delta H being negative. The other aspect we look at here is in this section right here, and we focus on the delta S. And we know that if you have increased chaos or increased disorder, that this is the natural order of things, according to the second law of thermodynamics, that as the longer a situation occurs, the more likely disorder is going to happen. So that positive value means that it's going to be disordered. Well, if you have a positive value here and you're subtracting a negative value with a positive value, and we know the temperature is in Kelvin, will always be positive. So this quantity is going to be positive. A negative minus a positive is going to be the ideal situation in which we create a spontaneous reaction. So, I was afraid that was still going to happen, so Smartboard and I just are not getting along. We can predict, based upon that idea, we can predict a way of calculating what temperature we can have that's going to change a non-spontaneous reaction, which means probably that the delta H is endothermic, into a spontaneous reaction. So we look at this reaction right here. Now, the values that we have in the charts, in the chapter, and at the appendix, are all what we call standard condition values for free energy, enthalpy, and entropy. And we don't necessarily have to put the circles on there, but the circles, the exponential circles, simply are telling us that this standard conditions of 1 atmosphere pressure, 0 degrees Celsius, or 290 or 273 Kelvin, and if it's a solution, 1 mole per liter. And what I'm going to do here is I'm going to rewrite this scenario here so that I have T by itself. So this is what we have here. First thing I'm going to do is I'm going to isolate the negative T delta S here. So I'm going to add a negative delta H to both sides, gives negative delta H with negative T delta S. And then to get the T by itself, I have to get rid of the negative, and I have to get rid of the delta S. So divide both sides by negative delta S, the negatives cancel out. And that gives us T is equal to delta H over delta S. And if we look at the labels like I was talking about before, delta H is measured in kilojoules per mole. Entropy is measured in joules per mole Kelvin. I need to convert that over to kilojoules so I can make this prediction, so the kilojoules will cancel out. And then when I do that, that gives me in the denominator a k in the denominator, and the denominator of a denominator becomes the numerator, and so this value is indeed going to be k. So we have to change our delta S values after you look at the numbers in the back of the book or in the chapter. We're lucky enough to find it there. And it's going to give us a value when you change the kilojoules per mole Kelvin to Kelvin when we calculate this out. So let's take a look at the example I gave you on the script there. We're looking at this reaction right here, magnesium carbonate decomposing to magnesium oxide and carbon dioxide. So we have to go to the charts and we find the delta S by taking MgL's delta S, which is 26.9, and the carbon dioxide, which is 214, which is a much higher number, which we expect a gas to be much higher than a solid, because gas is more random, solids are very ordered. And then we're going to subtract the magnesium carbonate value, which is 65.9. And we get 175 joules per mole Kelvin. But we want not joules, but kilojoules, so we just do a quick conversion, times 1 kilojoule with 1,000 joules. Joules cancel out to leave us 0.175 kilojoules per mole Kelvin. The delta H then, we do the same thing. MgO delta H, enthalpy value is -601. Now that's heat of formation reaction, how much heat it takes to create these compounds. And that's where these numbers are coming from. So that's -601 for magnesium oxide, -394 for carbon dioxide, minus 1,112 kilojoules per mole for the magnesium carbonate, and we end up with 117 kilojoules per mole. Now, if we go through and calculate that with the Kj values for both of them, we're going to have 117 kilojoules per mole divided by, that's a 0.175 kilojoules per mole Kelvin. That gives us 669 K. And since nobody has a Kelvin thermometer, we really should change that over to Celsius by subtracting 273, and we get 396 degrees Celsius. Okay? That's how the problems will be done. Find the values, change the entropy to kilojoules per mole Kelvin, and then do the practice problems. Practice problems is a little bit different, so just kind of focus on this. If you look at the script, it's pages 834 and 35. 59 through 62 all. That means not just even, do odd and even numbers as well. So 4 problems for that. Okay? Have fun.